So up till now, we have developed the idea of phase shifts, right? And we have tried to understand the scattering problem by essentially computing the phase shift. So basically, we have claimed that there is an ansatz for the outgoing wave e to the ikr over r times some scattering amplitude. And it is a scattering amplitude that we have to basically figure out. And the scattering amplitude can be figured out by understanding the phase shifts of the outgoing wave relative to the incoming. So starting from today, we will develop a new method of understanding the scattering problem. And this is basically setting up of what is called the Lippmann-Schwinger equation. Okay, so this is an equation that sets that basically tells you how to calculate the how to compute the form of the scattered wave, but it is a slightly it is not an equation in the sense that it tells you what psi is. It's actually what is called an integral equation. Okay, so we'll set this up and I'll explain what that means as we go along. Essentially, the way we'll be solving this equation is by appealing to perturbation theory. So we'll assume that the perturbing potential is small enough that we can understand the scattered solution in a series called the Born series. And when we do the Born series at the lowest order, when we do perturbation theory at the lowest order, we will essentially find that the scattering amplitude that the f of theta that we have talked about thus far is nothing but the Fourier transform of the potential. So at lowest order, there is actually a one-to-one correspondence between these two pictures, and we will try to develop what this means in detail as we go along. Now, there are certain mathematical prerequisites for understanding the stuff that we will develop. And I had a conversation with the mathematical physics teacher you had, and the way I will do this is by developing a very simple example so that you're reminded of the concepts that you already studied. And of course, as usual, if you have any questions, you can ask. No. So our starting point is, of course, the Schrodinger equation. So let us forget about everything about scattering and simply claim that we are trying to solve the Schrodinger equation. Of course, we are looking at a potential that admits scattering solutions. The Schrodinger equation, of course, is del square. Now we are still considering potentials that are rotationally invariant. So I will only have v as a function of the absolute distance r and not v as a function of r vector. Psi, of course, is a function of all three variables r, theta, and phi. So psi is a function of r vector equals e psi of r, right? Now I can rearrange this equation, and this part I will call H0. H0 is the potential that just involves a kinetic energy part. There is no potentials involved. So I can write this in sort of abstract notation as H0 plus V psi equals E psi, okay, in ket notation. Of course, if I take the inner product with respect to r vector, I'm going to get the equation written above. I'm going to rearrange this equation. So if you rearrange this equation, you get E minus H0 acting on psi equals V psi. Okay. So remember that H0 is an operator, V is also an operator in this language. So if I'm being technically correct, I will write it in this fashion. And E is, of course, E times the unit operator. Now I can write down a solution for this. The solution for this is psi equals some phi plus 1 over E minus H0 V psi, where phi is any solution, any constant vector that obeys the equation. Okay. So this is the solution of this equation, at least the formal solution of this equation. Of course, it is extremely useless the way it stands. It doesn't tell us anything, but it is a formal solution of this equation, and this is our starting point. We'll like to extract some more information about psi progressing in this manner. Now, if you're doubtful that this is a solution, the way you understand this is by acting the left-hand side with the operator in question. The operator in question is, of course, E minus H0. So E minus H0 acting on psi should give us V times psi. So take E minus H0 and act it on psi. This is the left-hand side. The right-hand side is E minus H0 acting on phi plus E minus H0 divided by E minus H0 V of psi, right? And since H0 phi equals E phi, phi is any vector that satisfies the free equation. The first term is of course 0 because E minus H0 acting on phi. E minus H0 is an operator that annihilates phi basically, and this is basically equal to V times psi, right? So this is a formal solution of this. Phi is simply a constant vector that obeys the free Hamiltonian eigenvalue equation. So to understand this equation, we need to understand something about the inverse of an operator. I have to understand what 1 over E minus H0 is. And we have never encountered such a thing in quantum mechanics before, right? So we've always thought of operators as acting on vectors and to give you a new vector. But how about the inverse of an operator? And how do you understand the inverse of an operator? The inverse of an operator can be understood in terms of what is called a Green function. So if I write this in coordinate space, then the way I would understand the inverse of any operator. So suppose if I have an operator A, right? Then the way I will understand the inverse is A inverse times something G is a delta function. Crudely speaking, A inverse, acting on. So G can be thought of as the inverse of A inverse, roughly speaking, right? Or if you don't want A inverse here, you can actually take A. If I construct an operator G such that A times G is just the unit operator, then I can think of G as the inverse of A in some sense, right? So if I write this in coordinate space, then the way I would write this is this operator times G, which is a function of, let us say, R and R prime, equals delta cube R minus R prime. Okay, so this is the coordinate space representation of the abstract equation written above. Okay, so this G that I have to find in order to determine the inverse of an operator is called the Green function of that operator. So this is the Green function of operator A. Okay, so essentially this boils down to understanding. To understand the operator 1 over E minus H0, I need to understand the Green function of the operator E minus H0. Now that is the first point. The second point is, even if I do figure out what 1 over E minus H0 is, this equation still doesn't give me psi, right? Because it gives me psi as an equation that also needs the knowledge of psi to compute it. So psi equals phi times something times psi is this equation, right? Psi equals phi plus some operator times psi. So if I have to figure out what psi is, I need to figure out what to feed in on the right-hand side psi, right? So this is, if I write it down in the Lippmann-Schwinger form, what I will end up with is what is called an integral equation. And the way I will understand this integral equation is by expanding this psi in orders, and by claiming that if I want to find psi to the first order, on the right hand side I can retain psi to the lowest order, which is 0. If I need to figure out psi to second order, then on the right hand side I would need the wave function to at least first order. So this is your typical trick for perturbation theory. So you can understand this integral equation as a perturbation series for psi. We will talk more about this as we go along. Okay, so this is. So basically, to understand this, we need to understand Green's function methods. And to understand Green's functions, you need the Fourier transforms and contour integrals. So to make us sort of comfortable with this language, even though you guys know this because you have studied this in your mathematical physics course, the way I will start this lecture is by doing out a very simple one-dimensional example where the calculations are rather straightforward. And they're straightforward, but they can still be easily adapted to our three-dimensional problem at hand because the structure of the differential equations are rather similar. So our starting point would be to solve a simple one-dimensional differential equation using the Green's function approach. So side or rather, it's not an aside really, it's an example. Okay, solving a simple one-dimensional differential equation using the green function approach. I will also calculate this Green's function using Fourier transforms, and I will not rehash Fourier transforms because I'm sure that you guys remember Fourier transforms, and we have used this extensively in a quantum 1 course. Okay. So the differential equation that we will start with is d square f over dt square plus, let's use y, omega 0 square y. Of course, if I write this equal to 0, this is trivial. You know that the solutions are sines and cosines, but I will complicate this slightly by writing f of t. Okay. So the way you understand this differential equation, again, if you have any questions at any point, please stop me and ask. The way you understand this differential equation is by claiming that this is a simple harmonic oscillator, all right, but there is also a driving force f of t on the right hand side. So in addition to the simple harmonic potential, there is also another force that is driving the pendulum, right? And this driving force is f of t. Now this term makes this an inhomogeneous equation because the y doesn't factor out completely, right? So if I can write an equation as some operator times y equal to 0, that is a homogeneous differential equation. Of course, this is an inhomogeneous differential equation. The Schrodinger equation, on the other hand, is actually a homogeneous differential equation because I can write the entire equation as something times I equals 0. Okay. So the fact that this is an inhomogeneous equation actually makes the interpretation in terms of the driving force easier, because if I also had a y here, I will have to interpret f times y as the driving force, which might be a little complicated, but this is what we would actually have to do for the Schrodinger equation case. But for this simple case, I only have a driving force f of t. And my goal is to solve this equation somehow. Okay, of course, I'm sure you guys know many methods to solve this equation, but we will be employing a particular technique using green functions. Physically, the way you understand Green's function is actually very simple. So think of this as an impulse that acts on the system, and think of y as the response of the system to this impulse. And this is not an unreasonable thing to do because y is indeed, y at any point is the height of the oscillator, right, as it moves. So the displacement, of course, is a function of the impulse. So if you drive it faster, it's going to rise up faster. So the response of the function is y, and the impulse that acts on this oscillator is f of t. So I need to calculate the response based on the impulse. Okay. Excuse me. So far, so good. Any questions? Is everyone able to hear me?
Yes, sir. Clear.
Okay, clear. Very good. Thanks. Because my internet connection is a little iffy, so that's why I wanted to make sure. All right. So the way I'm going to do this is postulate the following. I am going to divide this impulse, whatever this f of t is. This f of t can have some random form. I don't care. It's going to have some form like this. It doesn't matter. Now, I'm going to piece up this time into very, very small intervals. So, like this. Okay, something like this. Now, this is not an exact picture. I'm just giving you a picture to understand what's going on. That's all. So at every single instant of time, let us say I'm looking at some time t5 or t10 over here, right? The impulse is basically a spike at that particular point because I'm not worrying about other times. I'm only freezing my impulse at that particular time. So at that particular time, the impulse is a delta function. And responding to this delta function, the oscillator is displaced to some value y. So instead of solving this differential equation, I'm going to claim that I'm going to solve a different differential equation, one that involves a delta function impulse. I'm going to freeze the impulse at some particular time t prime. And I'm going to call the response to this delta function impulse as some g. Okay, so solve the equation for a delta function impulse. Okay, so let's call this g, and since I'm freezing the time at some t prime, I'm going to have delta of t minus t prime, and of course the response is also decided by that at that particular time, so the left hand side is also a function of t minus t prime. So I'm going to instead solve the equation d square g, which should be a function of t minus t prime, plus omega 0 square g equals delta t minus t prime. Okay. Now, instead of carrying this t minus t prime, I might as well call it a different variable, just t itself or some time tau. So I can write this equation as d square g over dt square plus omega 0 square g of tau equals delta tau. Okay. Now, what does this buy me? This doesn't seem to do much because, yes, you had an equation in which the right-hand side was f of t. Now the right-hand side is delta of t. And many people are more afraid of delta than f. So this doesn't really accomplish anything. Well, it does. It does accomplish something. It turns out that by employing Fourier, so it helps in two different ways. Essentially, if I can figure out g, I know y. Okay, so this might be a very tall claim to make, but it's actually very simple to see that if you know g, you know y. In other words, if I know the response of the system to a particular delta function impulse at any one single instant of time, I know the response of the system over a cumulative time with an impulse function f of t. Now, this is not really hard to see because if I understand the response at one single interval of time t, then the total response is basically an integral of this, right? Because I can piece up this f of t as a series of delta function impulses, right? From 0 to t or minus infinity to infinity or whatever it is, for however much time the impulse acts. So if I know g, I know y. I can actually prove this mathematically quite simply because I can write down the solution y of t as simply integrating. Suppose if I assume that the impulse acts from 0 to infinity, I'll have 0 to infinity. Okay, the limits are not really important because it depends on how long the f of t acts for, and that depends on who is switching it on and off. Anyway, whatever time for which the impulse acts, the cumulative response y of t can now be solved by doing a very simple integration instead of solving a differential equation. This is basically g of t minus t prime f of t prime dt prime. So if I know the Green's function for the operator d square over dt square plus omega 0 square, then I actually know what the solution of this equation is for any time t, for any impulse f of t prime. How is this true? Well, let us actually check if this is consistent. If I multiply both sides by the operator d square dt square plus omega 0 square, I should get f of t. So let's see. So d square dt square plus omega 0 square acting on y of t. If this is indeed a solution of this equation, then if I act d square dt square plus omega 0 square on this integral, I better get f of t, right? Now notice the integration is over a dummy variable t prime because I'm integrating over all times, right? So I'm not using the variable t, I'm using a dummy variable t prime. So the whole thing, the integral itself is actually a function of t with the integration variable t prime integrated over. So since the differential operator that is multiplying this is a function of t and not t prime, I can with impunity take this inside the integration sign. So I can write this right hand side as d square dt square plus omega 0 square g of t minus t prime f of t prime dt prime. Okay. Now notice that the one between g of t minus t prime and f of t prime, this operator can only hit g because f is not a function of t. So this is only going to hit g. But how does it hit g? We know that d square dt square plus omega 0 square g of t minus t prime is nothing but delta of t minus t. Okay. So I can write this equation again as 0 to infinity delta of t minus t prime f of t prime dt prime. And by the property of delta functions, you know that this is basically picking out the value of the impulse at time t. Okay. So if I know the green function of this operator, then I can simply do a very simple integration of this green function weighted by the impulse to get the response of the system at any other time. Okay, so this is the claim. So let me box this equation because this is, oops, excuse me. Okay, I cannot box this equation because I wrote it incorrectly, but this is an important equation. Okay. All right. So our goal basically now boils down to finding the green functions. If I find the green function, I have solved the differential equation. I hope I have convinced you of that. So let us move on to the next goal of, let us now figure out g of tau. Tau, I remind you, is t minus t prime. So let us look at the differential equation again. D square g over dt square plus omega 0 square g equals delta of tau. Okay. Now, g is of course a function of tau, and I'm going to solve this using the Fourier transform technique. So there'll be a whole bunch of stuff here. I'll first Fourier transform and I'll also do a contour integration. So all of this should make you very happy. So what is the Fourier transform in one dimension? And for the variables t and omega, the Fourier transform is defined as g of, or g tilde of omega is basically dt e to the, I think, I omega t, or is it minus I omega? No, it is e to the minus I. G of t minus t prime. Okay, or rather, I will just use tau consistently instead of getting confused. G of tau. Okay, and g of tau is 1 over 2 pi integral dt e to the I omega t g tilde of omega. Okay, so this is exact. Of course, there is different ways to define the normalization. I think you can also define it consistently as putting a 1 over root of 2 pi in both these equations, right? So I can define g tilde as 1 over root 2 pi of this, and g of tau as 1 over root 2 pi of this. Or you can put all the 2 pi's in one equation and leave the other one unharmed, like this, right? So they are both consistent. So please make sure that you look at whatever references you check carefully for what normalizations they put in. But of course, ultimately, all the normalizations in this particular problem is a little moot because the wave functions are only defined up to a normalization. So whatever normalization is, I can always absorb it in the overall normalization of the scattered wave function for this particular problem. But it's still very good practice to check your normalizations to make sure that they're at least self-consistent. So you cannot use this normalization in one step and a different normalization in the next step. So you should be careful of that particular fact. So what does the Fourier transform essentially do here? Well, the Fourier transform essentially makes this differential equation into an algebraic equation for g tilde of omega. How does this accomplish this? So to do this, please understand that the delta function also has an integral representation. So I should be using tau. Okay. dt e to the I omega tau. Okay. So this is all from minus infinity to plus infinity. So let us plug in the g and the delta in terms of their Fourier transforms. So on the left hand side, I have d square dt square plus omega 0 square g of tau equals delta tau, which can be written as d square dt square plus omega 0 square acting on 1 over 2 pi integral dt e to the I omega tau g tilde of omega. That is the left hand side. The right hand side is 1 over 2 pi integral dt e to the I omega tau. Okay. Oh, sorry. I want an equation. I want g to be a function of tau. So here I need to integrate over omega and not tau. Okay. Same here, because if I integrate over t, I won't get a function of t. I need to integrate over omega. If I want the inverse Fourier transform g tilde of omega, I need to integrate over t to get a function of omega. So I made a mistake here also. So both of these guys have to be integrations over the frequency and not the time. Okay. If I'm working in x and p, of course, the variable conjugate to x is p, of course. So I'll have a g of x and a g tilde of k, or something like that. Okay. So again, this is exactly what we did to figure out the momentum space wave function given a coordinate space wave function. All right. So again, since the integration on the left-hand side is over omega, I can take the operator inside. So I can write this as d omega d square dt.
Sir, I think it's not showing.
Oh, it is not showing. It is actually showing for me. Is everyone having a problem?
It's
No,
showing,
sir.
sir.
No. Okay. Then I will stop share and reshare. How about now?
Yes, sir.
Is this showing everybody?
Yes, sir.
Okay. Thank you. All right. So now the only time that is there on the left hand side is the e to the I omega t part. The g tilde is only a function of omega. Of course, d square dt square acting on e to the I omega tau. Tau is just t minus prime, is nothing but minus omega square e to the I omega t. So the left hand side can be further written as d omega minus omega square plus omega 0 square e to the I omega t g tilde of omega. The left hand side I will not do anything. Sorry, the right hand side I will not do anything. I'll just keep the delta function as such. Okay. Now notice that this gives me the inverse Fourier transform in a very straightforward fashion, because I can write this entire thing as the integration is over the same variable omega, and the integrand e to the I omega tau is a constant, is the same on both sides. So I can write this equation as d omega minus omega square plus omega 0 square g tilde minus 1 e to the I omega tau equal to 0. Okay. And if this has to be 0 for every value of omega, because g tilde is some function of omega, if this has to be equal to 0 and e to the I omega t is a non-zero function of tau, then the stuff multiplying e to the I omega t has to vanish identically, right? So the only way this can be satisfied is if minus omega square plus omega 0 square g tilde equals 1. Okay, so essentially it is boiling down to an algebraic equation for the inverse Fourier transform. The inverse Fourier transform g tilde of omega is nothing but minus 1 over omega square minus omega 0 square. Simple. In fact, we will find something very similar in the three-dimensional case also, because the structure of the differential equation is very similar. Okay. So essentially what we claimed is that if I know the green function, I know the solution to the differential equation. Now I have figured out the green function, but I'm close, but not really close, because I've figured out the inverse Green's functions, right? So inverse Fourier transform. So I need to figure out the g of tau. G of tau, of course, once I know g tilde of omega, g of tau is given by the simple integration. So g of tau is 1 over 2 pi integral d omega e to the I omega t, excuse me, g tilde of omega. Okay. Now, this is a simple integration, but of course it involves some contour integrations, as you will quickly see. So this is equal to 1 over 2 pi d omega e to the I omega tau divided by, so I'll put the minus sign outside and write this as omega square minus omega 0 square. Now, do you guys remember solving such integrations using the contour integration technique? Yes?
Yes, sir.
Okay. So I'll quickly revise what that is in case some of you don't remember, or at least for completeness sake, it's useful to understand how to do this. So the way you understand this is, of course, when on the real line, this blows up at omega equal to omega 0, right? So the way you actually understand this integration is by shifting over to the complex plane. So you artificially make omega a complex quantity. So I can write this integration d omega e to the I omega tau over omega square minus omega 0 square as d omega e to the I omega tau. Now I'm adding some small imaginary quantity I epsilon. So this is a so-called I epsilon prescription. So basically I'm converting what was a real integral into an imaginary integral. So if I do this, I have to be careful, because now if I pretend that omega is an imaginary quantity, and if I'm integrating in the complex plane, and if I choose some contour, I have to make sure that the contribution to this integral from the imaginary parts of this contour is actually very small. So I'll have to choose the contour in that particular fashion. I'll demonstrate what this means. Now, the way you understand this I epsilon prescription is as follows. So imagine that basically I'm making omega complex by hand. So in the denominator, I have omega square minus omega 0 square. So let us add omega, let us say plus or minus I epsilon minus omega square. So this is basically what I mean by making omega complex. I'm adding a small imaginary component to omega. Of course, in the final result, I will take epsilon to go to 0. So these things shouldn't matter, but I'll have to take the limit carefully. So what is this? This is equal to omega square plus minus epsilon square plus minus 2I epsilon omega minus omega 0 square. And since I'm going to take the limit epsilon very close to 0, I can always neglect the epsilon square term. So this is basically equal to omega square minus omega 0 square. And now since epsilon is very, very small and it is in my hands, I will call the quantity 2 epsilon omega as another small quantity epsilon. Okay, so plus minus I epsilon. So if you want, I can call this epsilon slightly differently. And I've made the identification that 2 epsilon tilde omega is the new infinitesimal quantity epsilon. Okay. If I choose epsilon tilde small enough, I can always pretend that 2 epsilon tilde omega is also small. So this is the sense in which I am adding this I epsilon here. And remember that I can either add plus I epsilon or minus I epsilon. And if I do these, I'll get different pole prescription in general. So in this particular problem, I'm choosing minus I epsilon. And in the original Schrodinger equation problem, I will choose again a minus I epsilon. I'll explain what this means. So if this is not a trivial point, if I choose plus I epsilon versus minus I epsilon, my poles would be different in the complex plane. So my answer to this integration would be different. My green function would also be different. Now, this plus and minus I epsilon itself is not physical, but the green functions that you get after doing this integration is indeed physical. So you'll have to make a choice at that point, depending on certain physical arguments, which one of the green's functions you want. If there is nothing wrong with either green functions, you should take both the green functions as a solution. But if on physical grounds you're able to argue that one of the green functions, maybe the one that comes from the plus I epsilon prescription is bad for some reason, you can throw away that and simply choose the minus I epsilon here. So whatever this is, there is a freedom at play here, which you should use carefully. And this technique is usually called the I epsilon prescription. Oh man, sorry. Okay. It's called the I epsilon prescription. So let us actually go back and solve our Green's function. So, excuse me, g of tau is now given by minus 1 over 2 pi e to the I omega tau divided by omega square minus omega 0 square minus I epsilon. Okay. Are there any questions about any of this? So I can write this as minus 1 over 2 pi omega minus times omega minus or omega okay. So I can factor the denominator this way. So again, if you expand the denominator out, this is a plus b times a minus b kind of deal. So this is a square minus b square, right? So this becomes omega square minus omega 0 square. And I'll throw away the epsilon square piece. So the cross term is basically minus I epsilon omega 0, which I will again call minus I epsilon. Okay, it really doesn't matter because if epsilon is small enough, I can absorb the omegas into the epsilon. So this is exactly the same as what I have in the denominator. The denominator can be factored in this fashion. So if I do it this way, I can solve this integration very easily. Okay, I don't have to. So in the real plane, this was a little difficult because in the real plane, if something blows up at omega equals omega 0, of course, there is a way to approach this problem also using what is called the principal value of this integral. But in the complex plane, there is actually a ready-made prescription available because we are not scared of infinities in the complex plane. We simply apply the Cauchy theorem, right? So let us now do this integration, realizing that I'm doing the integration in the complex plane by making omega complex. So now I have two simple poles. Two simple poles. One at omega equals omega 0 plus I epsilon, and the other at minus of omega plus I epsilon. Okay. Any questions about this? Okay, so let us draw the complex plane, complex omega 0 plane. So this is my complex omega plane. So this is of course the imaginary omega axis, and this is the real omega axis. Excuse me. This is the real part of omega, right? So where are the two poles? So remember that in this quadrant, the real part of omega is positive. The imaginary part of omega is also positive. Here, the real part of omega is positive. The imaginary part is negative. Here, the real part is negative. The imaginary part is positive. Here, both the real and imaginary parts are negative. So the first pole is at omega 0 plus I epsilon. So omega 0 is, of course, real, and plus I epsilon is in the positive quadrant. So this pole is, let us say that this is my omega 0 and this is my epsilon. So this pole is right here. So this is the point omega 0 plus I epsilon in the complex plane. Okay. The real part of omega is omega 0. The complex part of omega is epsilon plus epsilon. The other pole is the real part is minus omega 0 and the complex part is minus I epsilon. So that guy is over here. These are the two poles in my complex plane. Now, if I have to do the integration, of course, I have to choose a contour, right? How will I choose my contour? Now, there is multiple choices available. A priori, there is no one contour, right? I can choose a contour like this. Now, if I choose a contour like this, I will get 0 because this guy has no poles. So I will get a trivial Green's function equal to 0. My response will be equal to 0 and I have not solved anything. So I should choose a contour that gives me a non-trivial Green's function. The only way I can choose a contour that has a non-trivial Green's function is if I encircle one of the poles. If I enclose one of the poles, then of course I can use Cauchy residue theorem and I can claim that the integration, whatever the integral I is, this is basically 2 pi I times the sum of the residues, right? So this is the Cauchy theorem. I hope you remember this. Okay. So then if I choose a contour that is in the top half, I can choose the pole at plus omega 0 plus I epsilon. If I enclose the contour in the negative plane, I will enclose the contour minus I omega 0 minus I epsilon. But enclosing it in the negative part of the complex plane is actually problematic for this integration. Why? Because remember that I made omega complex by hand, right? So which means that omega, which was a real quantity, now has, so omega, which was initially a real quantity, excuse me, wrong color. Omega, which is a real quantity, now has a real part plus an imaginary part. Okay. Now, if I choose the contour on top, let us say, then let me claim that I'm choosing the contour such that I'm starting at r equal to the real part of omega equal to infinity, and I'm going by an infinite semicircle and reaching at r equal to minus infinity. Okay. So like this. Okay, so this is of course a terrible drawing. This is right at the center. So okay. Now the radius of the semicircle is of course some r, which is also an infinite radius. Now the integrand has an e to the I omega tau, right? So if you go back and look at it, the numerator has an e to the I omega tau, which means if I choose the radius of the semicircle to be very large from very large parts of this complex omega plane, this is going to have a contribution e to the I omega real plus I omega imaginary, and the omega imaginary value is, let us say, some r. So I'll call this radius some r. Tau, and this is basically equal to I omega real tau minus r tau. So if I take the radius of this circle to infinity, then of course the contribution from the imaginary part basically goes away. And this is basically dominated by the real part of the integration. Okay. So this is why I want for this particular problem to close the contour on the upper half. If I close the contour on the lower half here and pick up the pole at minus omega 0 minus I epsilon, I run the risk of having an infinite amount of contribution from the imaginary part of the integration, because if I close the contour on the, if I close the contour on the lower half, then e to the I omega t will go to e to the I omega real. And since in the lower half, the imaginary part is negative, I'll have minus IR times tau, which becomes e to the I omega r tau times e to the r tau. So I'm getting an infinite amount of contribution, excuse me, from the imaginary part of the complex plane, and I don't want any contribution from the imaginary part of the complex plane, because the imaginary part in the omega is something I introduced by hand to make my life easier. So I don't want an infinite amount of contribution from the imaginary part of the plane, because ultimately omega is a real quantity. So I'll have to only calculate the uh, contribution from the real part. So I'll have to, from physical grounds, I'll have to close the contour on the top for this particular problem. If I close the contour on the top, I pick up only one pole, and that pole is at omega 0 plus I epsilon. So what is the residue? Residue at omega equals omega 0 plus I epsilon is of course given by, it's a simple pole. So I'll have to multiply by this quantity the function omega plus omega 0 plus I epsilon, right? So this is the prescription to calculate the simple pole. At the pole at z equal to a is given by z minus a times the function. Of course, since it is a simple pole, the infinite parts neatly cancels with the overall multiplication. So for this particular guy, I get this is equal to I at omega 0 plus I epsilon, I get omega 0 plus I epsilon times tau divided by, this is of course twice of omega 0 plus I epsilon, because I have omega plus omega 0 plus I epsilon. So this is basically 2 times omega 0 plus I epsilon, because I'm evaluating at the point omega equals omega 0 plus I epsilon. So when all said and done, what is my g of tau? My g of tau for this particular problem is minus 1 over 2 pi times 2 pi I times the sum of residues. There is just one residue because on the top half there is only one pole. Limit epsilon going to 0, e to the I omega 0 plus I epsilon times tau to omega 0 plus I epsilon. Okay. Excuse me. So which tells me my g of tau is the 2 pi cancels, and I get a minus I limit epsilon going to 0, e to the I omega tau, e to the minus epsilon tau divided by 2 times omega plus I epsilon. Now taking the limit epsilon going to 0 is trivial, because e to the minus I epsilon goes to 1. So my Green's function is given by minus I. Okay, so this is the Green's function for the driven simple harmonic oscillator problem. Now, of course, if you are given some other extra conditions like the response, so if you're also supplied some boundary conditions like the response at t equal to 0 is 0, at something like that, then you can use these boundary conditions to refine the Green's function further. So suppose if you are given that, let us say g of 0 equals 0 or something like this, okay, then you can use these boundary conditions, and I can write this e to the I omega tau as cosine plus I sine. Of course, if I want g of 0 to be equal to 0, the sine part becomes 0, but the cosine part is not 0. So I should have to basically throw away the cosine part and retain only the sine part. And I can write this as basically sine omega tau divided by 2 omega or something like that. Okay. But in the absence of these boundary conditions, this is the most general form of the Green's function that you can write down for this particular problem. And of course, once I have the Green's function, the response, the total response, of course, is dt prime g of t minus t prime f of t prime. Okay, so that can be accomplished by a simple integration. So the method of solving differential equations using the Green's function technique amounts to basically 3 steps. The first step is converting the given differential equation into an algebraic equation for the inverse Fourier transform. Okay, inverse Green's function, g tilde of omega, or in the xk case, g tilde of k. The second is by using epsilon prescription or some other contour integration technique, solving the contour integral to give you the actual Green's function in time space, g of tau or g of r in the Schrodinger equation case. That is the second step. The third step is, of course, using this Green's function to construct the solution, which in our case is basically integrating the Green's function with respect to f of t prime. F of t prime is the driving force. Okay. So in the going back to the Schrodinger equation case, we will follow the exact 3 steps, but the last step would be a little complicated because the driving force in this case itself involves psi. So you remember that since it's a homogeneous differential equation, the driving force, if you assume that potential is the impulse, it is not just the potential, it is the potential multiplied by the wave function, right? So in the very last step, we will have a slight complication. The first 2 steps will go on exactly the same way. I'll figure out the Green's function. Tomorrow I will do this problem. I'll figure out the Green's function in the K space. Then I will do a contour integration just like we did now to figure out the Green's function in the R space. And once I write down the Green's function in the R space, I'll have to write down the final solution. Of course, in the final solution, I'll have to write dr prime, g of r minus r prime, v of r prime times a psi of r prime. So the equation for psi of r on the left also involves psi of r on the right. This makes it a slightly more complicated equation. It's an integral equation for psi, and then we will discuss how to solve this. So please go through this part very carefully today, and we will use these results to do the 3-dimensional case tomorrow, and then we will set up the Lippmann-Schwinger equation tomorrow. Okay, so we'll stop here for today.